So today we're going to look at regressions and the corresponding correlation coefficient. So for us, the regressions that we'll be doing are linear, which means we are going to be finding equations of lines to best fit data. Now, you should know that lines are not always the best sort of equation to pick, but for us, that's what we're going to focus on. You should know, however, that you could choose a different type of an equation to model your data if it seemed like something else would fit. For instance, a lot of the COVID data that you can find online right now is not at all linear. It is exactly exponential. So you could do an exponential regression instead of a linear regression. We just don't have a hypothesis test to test how well the data fits. So the statistic and the parameter that we use that corresponds to this regression is this correlation coefficient. So before we get there, let's just talk really quickly about linear functions. So that's equations of lines. So, right, just y equals mx plus b. Our calculators aren't going to use m, and I think they switched, they actually put a b over here. We'll see when we do it. But that x coefficient, so usually it's played by m. This is the slope, right? It tells us how steep or flat the line is. And then b, that constant term, that is the y-intercept value. Okay. And some things to think about, right? Slopes that go up to the right, slope is positive. And if it goes down to the right, the slope is negative. Right. And the steeper the slope is, right, the larger the number, the larger your m value would be. Okay, so that's kind of all. You won't have to find the equation of a line. Our calculators are going to give it to you, but in case you were trying to refresh your memory, right, if you wanted to find the slope manually, that's the way. Okay, so on to the statistics. So the correlation coefficient, this variable that we're going to look at, this is a measure that tells us, right, how strong the linear relationship is. How well does our line seem to fit the data? Okay. So the population symbol, so it's a variable that's going to have a parameter and a statistic. So the population symbol, remember that's the parameter, is a rho. So it's kind of like a curly P. It's the Greek letter rho. So then likewise, so that this is a rho, I think you can guess, right, that's an R, a Greek R. So the sample symbol, so the statistic is an R. And the properties of rho and R, so they're always going to be between plus and minus 1 and inclusive. They can equal -1, they can equal +1. And something, oh, here, it's down here on item 4. Let's see, so I'll go down in order. It's sensitive to outliers. Hopefully that's not going to be an issue. I'll show you what one of those might look like. The switching of the x's and y's does not change the value, again, of rho and R. And then here's the one, the sign of m and r are the same. Other than that, the values aren't related, but if the slope is positive, then the r value is going to be positive. Remember, it can go between plus and minus 1. So if it's close to -1, then your slope would be negative, right, going down to the right. Right? And if it's close to the actual -1, then most of the points are going to be on the line. If it actually equals -1, then all of the points are exactly on the line. If it actually equals exactly +1, then the slope is positive and all of the points are on the line. Okay, so I just have some graphs down here. So if you had to guess, right, which one of these had an R value, right, that's positive, right, so that would be this one right here. It's not an awesome line, but you can kind of imagine where you could fit a line through there. And we're not going to be doing guesstimating. We're going to have our calculator show it to us, and I'm going to show you how to do that. So for this one here, right, your slope is positive, and so your R value would be positive as well. And it's going to be, you know, well, I don't know what it would be, but it would be close to 1 because those are pretty good. Now this next one, there you can tell, right, the line that would go through those points is negative, so the slope would be negative, and the R value would be negative. And not only negative, but that's going to be really close to -1 because those points are really, really well lined up. Now this third picture, you can see it just looks kind of like a little snowstorm. I mean, maybe if you had to guess, it would be negative-ish. Maybe that one? It would be really hard to say, but this, maybe the slope is going to be negative, but that R is going to be super close to 0, right? There's not much of a relationship in there. Okay? So the closer R and rho is to 0, right, there's not a linear relationship. Right? The closer it is to plus or minus 1, the stronger that relationship. Okay, so let's go ahead and try some out. So I have some data for us to use. So this is the life expectancy based on the year that you were born. Okay, so if you're born in 1950, and it's for white women born in the US. So if you were a white woman born in 1950, you can expect to live 72.2 years, okay, and then so forth. So we're going to do I'm going to show you how to do this on your calculator. And the first thing we're going to do is a scatter plot. So a scatter plot, that is what you saw right here. These are scatter plots. Okay, so it's just a plot of the actual data. So these are your X values on the horizontal, and those are your Y values on the vertical. Oh, and I said sensitive to outliers. So item 2, right here, sensitive to outliers. Sorry, coming back. So if you looked at that first graph, actually, let's look at this one where we have a really great relationship between our X and the Y. If I would have had an extra value up here, an extra data point that's not like the others, well, that's going to throw my line off. It's going to pull that line really far up here, and it's going to change that slope significantly. Okay? So if you have one value that's not in line with the rest of them, that can really throw off your data. So it might be a case that if you do have one of those points, you might take a look at it and say, oh gosh, I think that might have been a mistake, or do I really need to, does that need to be included? Okay, so let's go ahead and take a look at this. So I have some screenshots for you, and I'll go ahead and bring my calculator up, but these are the things you're going to shoot for. Okay. So you're not going to be able to see my calculator and those things, so go ahead and cover this guy up. So the first thing you want to do is input the data, and I have mine in L1 and L2, and something you might want to notice, look at my L1. My first value is 0, so that's corresponding to 1950. So what I've done is I've let my X values, so my X values are the years since 1950, and then the Y values are the life expectancy for white women. Okay, so move that over so you can see what I wrote. So go ahead and grab your calculators, and mine is already input in here because, actually it's probably not. So here we go. We're going to go to Stat and Edit, and then go ahead and grab yourself some lists. Clear them off. So I'm going to put, 1950, so the years since 1950 for this one is 0. So it's just 0. And then 1960, that's 10 years after 1950. 1970, that's 20, and I'm just going up by the decades. 30. 1990 is 40. 50. Okay, then I jump up to 64, and then 67. And then in L2, I'm going to put the corresponding life expectancies. So it's important that they correspond. So 0, that's going to have that 72.2. And 74.1, and 75.6, 8.1, right, making sure that they're across from each other. Okay, now so that's the first screen you see. The next screen that you see, you want to set your window so that you can actually see all of this data. So I'm going to go, the window is up here, it's the second button in. So second button in. So X min in your screen that you're going to see, right, your scatter plot in here, you can kind of see your picture here. X min is that furthest to the left number that you'll be able to see. And X max is the furthest to the right number that you'll be able to see. And then X scale, that's how much space is between each of those hash marks that you can see along the bottom. And then, right, Y min, Y max, same thing going that way. So now let's look at our data. So my X's are going to be my L1, and they go from 0 to 67. Okay? So I usually like to have a little bit of a buffer, so I'm going to do that. I'm going to go from negative, and to do negative numbers, right, you have to use the change sign key down here at the bottom. So I might go from negative 10 up to 70 for my X's. So it gives me a little buffer on either end. For my Y's, which I have an L2, right, it looks like my about 72.2 is my smallest value. So again, I'm going to give myself a little bit of a buffer. Oh, X scale, what do I want to do? I think 10 is pretty good. You don't want to have it too small, or you just get a solid line across the bottom. We're not going to use it really for like reading off points because they're not labeled on our calculator, but it's just kind of nice to, right, if you kind of know they're stepping by 10. It's like, oh, okay, well, that's about. Okay, so by 10, and then Y min, think about what your smallest value might be. I think I'm going to go 7. Well, here, let's see what I chose on here. Oh, I did 0 to 80. I guess I could do what I had on here. So 0 to 80. I'm sorry, I forgot I had one of these that I did on my calculator on my computer. Y min 50 to 90. This is not the only version you could do. Y scale is 5. I don't mess with the rest of that. Oh, look how it's the same. That's interesting. Okay, so now I have my data in and I have my window set. So let's see, what are we going to do? We're going to make a list of values. So we're going to input the data. And then we're going to set the window. And then we're going to turn on a stat plot. So to turn on the stat plot, so that is right here by the Y equals screen. And notice it's in blue, so we'll do the blue button first and then the Y equals, and it brings up that screen. And we want to turn one of these on. So yours probably look just like mine, they say off. So I'm going to go ahead and select Statplot 1. And since it's right, the off is highlighted, I want the on to be highlighted, so I'm going to hit enter. And then these are the different graphs that your calculator will do for you, and the Scatterplot is that first one that it's flashing on. So I'm not going to do anything. Then you tell your calculator where you put your data, and if you want to choose a color, if you have that option, go ahead. So that's all. Now it's all set. Right? Looks just like the next screen. And now the next thing we're going to do, and you know what, I bet I have other things in here, so I guess, hold on, I'm going to do something real quick. Yep. Okay, so I just got rid of my Y equals. If you want to do the same thing, sorry, I did that quickly. I went to my Y equals screen, right here, Y equals. And if you had anything like I did, you can just use the clear button, and it will clear that out. And now go ahead, and once you have your calculator ready, go ahead and hit the graph key up here on the top. And there's your scatter plot. So this is the data, okay, for life expectancy versus year you were born. So this is year born, and this is life expectancy, if we labeled our axes. Okay, well that looks pretty darn linear. So if I had to guess, I would say this is going to be, right, a positive slope, and I bet that R value is going to be close to +1. Okay. So when we want to actually test that relationship, right, we're going to test that R. There are 3 different methods. I'm only going to show you one. You're welcome to look the other 2 up. The first one, so I'm not going to do this one. This is the one I'm going to do. The other 2, you can do a traditional method. You use the t-distribution to get your critical values. Your degrees of freedom is the number of data points minus 2. So not like the individual numbers, but the number of points minus 2. And then to get your test value, It's this formula right here. It's not too bad. It's totally doable. The t-distribution is super easy to use. The p-value method, so this is using the stat test option on our calculator. I'm going to do that. There's a linear regression t-test. That's what option F is. So that's the one that we're going to be doing. There's a third option. It requires a special table that gives you the critical values for rho. It just has for alpha of 0.05 and 0.01 maybe. And I say something on here in pink sheets. That's something when we used to meet face to face, I handed out sets of the tables, the graphs. And I'm not doing that. So if you have a book, you can find this one. It's totally not worth it because, we get the p-value for free on our calculator. So let's go ahead and do a bunch of these. Well, okay, let's do 2. So your hypotheses. So it's going to be a hypothesis test. Okay, so with all of those things that we do with our hypothesis tests. The null hypothesis, remember hypotheses are about the parameter, so we use the rho symbol. So the null hypothesis is that rho equals 0. And remember, if rho equals 0, there's no relationship. Okay? So there is no relationship between the variables in the population. The alternative, so we can't say that it's 1 because we can't go past 1, so that kind of limits us. So what we'll just say is that it's not 0. So what our idea is are we far enough away from 0 to say that, oh, well, there must be a relationship. Okay? So if we're far enough away, there is a relationship between the variables in the population, and that's always going to be our claim. Okay, so again, I've given you the screenshot, so we're gonna aim to get these guys right here, but let's go ahead and do the hypothesis test. So H naught, rho equals 0. There is no, and I'm gonna go ahead and use the real words here. There's no relationship between year born and life expectancy. I'll just write it for 1, I guess. Rho, or H sub 1, rho does not equal 0, which means there is a relationship. Okay. So then, calculator. So you want to go to this vars and then y-vars function y1 and then calculate. Oh, I guess that was too fast. Sorry, we were done. Doing that vars y-vars, what it did is it took that information and it plugged, here I'm going to show you, go back to your y equal screen. It put that equation of the line here. Okay, so I'm sorry, I'm going to go back, stat, test, linear regression t-test, yada, 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 yada. Here we go. And this looks like, is it the same? It is, awesome. So at the top you see we have y equals a plus bx. That is our key. That tells us who these things are. So our line of best fit, so line of best fit, and I do LOBF for line of best fit, is y equals a, which is 73, plus b, which is 0.13, x. And x is, again, the years. Oh, I haven't said that yet. X is the years since 1950. And y is the life expectancy. Okay, I'm getting all the things in here. All right, so let's see. There is your test value. So that 10 point, so they have the same screen, so I'm going to look up here. So here's your test value. That t equals, remember we're doing a t-test. And then that next one is the p-value. That's what we're going to base our decision on. So that p-value, remember it's got that -5, so our p-value is 3.77 times 10 to the negative 5. Look over here on my second screen. So you can get to that on your calculator by using the down arrow. Okay, this little down arrow right here, if you just use the down arrow here, you can go down farther and see the rest of it. Notice my R value right here. Look how close that is to +1, right? This is a really, really strong relationship. And right, and that makes sense because that p-value is super, super small. So this is way smaller than any alpha, even though I didn't give you an alpha. So our decision would be to definitely reject the null hypothesis. And there is a strong, and I'm going to go ahead and modify this, strong positive relationship between year born and life expectancy. Now, I've kind of run out of room, but something that you should know, once you have a line of best fit and it's good, right? If you get to reject the null hypothesis, that means you can use this line of best fit to make predictions. So, if you wanted to see your life expectancy, you'd have to figure out, right, the number of years since 1950, since when you were born, and then plug that in for X. Okay? So, and then that would be your prediction. So you could do like a Y prime of 25 if you were born in 1975, and you would do 73 plus 0.13 times 25. Oh, that's right. To get that last screen up here, all you need to do is go to graph, because it's going to put, right there was your scatter plot. And remember we had it put our regression equation right here. This is the regression equation. Line of best fit is the same thing as regression equation into the y equal screen. Okay, so we're going to do one more, and we're going to do it quick. So let's go ahead and input this next set of data. 1975, 2016, we'll start at the top. Sorry, just inputting. So women's pay is a percent of men's. So we're doing a hypothesis test. So let's go ahead and X is going to stand for the year. Y is going to be the percent of women's pay. We're going to define our variables. We're going to write our hypotheses in symbols and words. There is no relationship. Null hypothesis, there is no relationship between year and women's pay percentage. How about that? And then H1, rho is not equal to 0. Oh my gosh, writing. There is a relationship. So we have the data in. Our stat plot's already set up, so let's go ahead and just fix our window. So now let's look at the X values that we're going to see. I did not scale them this time. So the smallest value we need to see is 1975. So I might go 1970, and I might stop at 2020, and 10 sounds good still. And then these values, how about 50 to 90? That still looks good. And I'm going to go ahead and clear out my Y equal screen and hit graph to get your scatter plot. Do they look linear? They look pretty linear to me. So let's go ahead and run our test. So stat test. Coming up from the bottom, linear regression t-tests. I haven't changed any of those. Look, it still has my regression equation, so that's nice. I don't have to go find that again. And there we go. So let's see. There's that p-value. is again 1.06 times 10 to the negative 5, super duper small. So again, our decision, we're going to reject the null hypothesis. Summary, there is a strong, and let's see, is it positive or negative? So let's look, our slope is positive, so it's a positive relationship. Strong positive relationship between year and women's pay. And let's go ahead and find that line of best fit. Let's find that relationship. Y equals a line of best fit. Y equals, what do I have there? A is negative 1010, and then plus 0.54x. So if we wanted to use this, since it's a good relationship, right, we rejected the null, there is a relationship, we could use this to predict for 2020. So if we wanted to know y prime of 2020, so let's go ahead and go to graph. I'm going to show you one more thing. So graph, there's our data. Here comes our line of best fit. Okay. So now, so here where it says trace, I want to do that calc option that's right above it. So second calc, and then we're going to do value. So just hit enter and put in the x value. See down here at the bottom it said x. So we're going to put 2020. And it tells us what the y value is. So 84 cents to the dollar. So in 2020, our data predicts that women will make 84% or 84 cents to the dollar for what men make.